Welcome to the week 4 live session that will be from 6 to 8 p.m. Hello, everyone. I'm Jyoti Sharma, and I will be taking this live session for the course Climate Change Extreme Event. And the course is instructed by Professor Soumya Savankar from IISER Bhopal. Uh, this is my brief introduction that right now I'm PhD final year student from IISER Bhopal, and I had my master's from Forest Research Institute, and my undergraduation was from University of Delhi. I also cleared UGC NET GRF and ICR NET. Along with that, right now I'm a PMRF research fellow, and that's why I have responsibility to teach for 2 hours every week. Along with that, I also have past NPTEL experience of teaching. So I already have taken five such live session for 5 different courses. The list has been given to you. Okay, so again, I just want to give you the instruction that we have a lot of MCQs question, and with the discussion, we try to find out the solution, which one is the correct answer, and based with that, we try to understand the concept. So for this course, we will try to learn the concept for climate change and extreme event, and that's how I will encourage you to write in the chat box the right option. And so this is how this will be the win-win situation. I can also learn from you, and you can also learn from my experience. uh, so what we have covered till now, for the week 1, it was very simple that we try to differentiate what is the difference between weather and climate. What do you mean by climate change and what is climate extreme? So what we learned is that uh, uh, the long-term statistics of the weather is known as climate. If there is a change in that statistics, and the statistics mostly is taken for 30-year based on 30-year data set. So if there is a change in mean, or let's say the change in the variability, then we can call it as climate change. And climate extremes are the some rare event, and if we have probability density function, then we will learn that in the tail we do have climate extreme. So this we learned in week 1. In week 2, we started with some example of climate extreme. So heat wave, cold wave, how we can define heat wave and cold wave. Then precipitation extreme, in which uh, we may have extreme rainfall, and we may also have drought conditions. So we learned about it. And then we talked about tropical cyclone, how it formed, uh, and why we are categorizing it as also climate extreme. Then we started with the data for in the week 3, what kind of data we have for this uh, to study the climate extreme. We talked about observational data set, we talked about reanalysis data set, and we also talked about the climate model based data set. What's the difference between three type of data set? Even if you don't remember, just let me know. I will give you some brief about this data set. Then we talked about data collection and processing. As I told you, uh, there may be some situation, or for example, in the Himalayan area, we do have we have very few stations, so there may be gap in the data set. So how we can fill it? Or sometime it may be happen that we are changing the sensor in the satellite, so that's how there may be difference in the value. Or sometime sensor may give you the wrong data as well for some pixels. So how we can correct it, uh, how we can firstly how we can fill the gap if somewhere if sensor was not working for 2 days, then there will be the gap. So how we can fill that gap, we studied about it. Then there may be some error, maybe due to different sensors we are using. So different sensor may give you the different value, so that's how there may be some error. And the temporal biases, we talked about these things and how we can correct. Then we talked about the climate model because we want to know what will happen in the future. um, Whether our frequency intensity will be increased in future or not. That's why we need climate model, and this climate model are based on some mathematical equations of your physical atmosphere. So based on that, we can have the climate data even for the future and even for the past, for the historical. And but the climate model is dependent on uh, the kind of data set that we are getting from the climate model will be dependent on what type of climate data model it is, what is the resolution. We have GCMs, that is global climate model, where the resolution is very coarse. Then we have RCM, regional climate model, where the resolution is finer than the global climate model. And we have different application of different climate model. So we talked about these things from week 1 to week 3. If you have any doubt, please write in the chat box. I can clarify this. Uh, After that, we will start with probability distribution. And this is very important. But before that, you must know climate extreme and about the how like what different kind of climate data we have. We may have data time series data sets. Let me draw it. Okay, so what kind of data we can have? For example, it is a Delhi. Okay, so we are considering Delhi as a point. Okay, so for that point, we may have temperature data. And let's say each day we have some values. So what we can say that for 1 year, we have 365 values. So if we are plotting it, so we have to rely either on this line plot or scatter plot, something like this. So this is temporal data we have. So what we are calling it as the temporal data. But what if we are considering Delhi not just as a point, but we are dividing Delhi into different grids? So let's say this is Connaught Place, this is Burari, this is, let's say, airport area. I'm just giving the example. So uh, different land use in we have different land use in Delhi, and that's why within Delhi we may have different grids. Okay, for each grids we will have data. So for each grid we will have 65 values, right? For each grid we will have 65 values for 1 year. 365 values. 365 value for this grid, 365 values for this grid. And that's why this is not just the temporal data, but this is also spatial data. Spatially, you also have data. Uh, okay, so that's how the data that we can have is either we just have yearly data set, or we may have spatial plus temporal data set. So let's say we have Delhi in 9 grids. So for 9 grids, we have, for each grid we have 365 values. And if we want to see how at each grid the climate is changing, so we have to calculate the same thing for each grid. Okay, so this we can do in for loops, either in Python we can do, or we can write some script, shell scripting. So we can do this is easy to do, but this is special thing that we can do. Okay, so these kind of data we have. Based on these data, we need to extract some information. So how we can extract some information? So for that, it is very important to learn about probability distribution. Okay, but before that, let me take one question that Geeta Anjali asked me. Ma'am, extreme climatic places, uh, explain. What kind of places you are talking about, Geeta? I didn't understand. At any places it can happen actually. So for example, I'm giving you one example. Let's say Rajasthan. I'm taking the okay, I understand what you want to ask. So it can happen over India anywhere, the climate extreme. So for example, in Rajasthan we have Rajasthan is characterized by high temperature, right? High temperature and low precipitation, low rainfall. But with the climate change, what is happening? That Rajasthan is also getting a lot of rainfall. So what will happen if it is getting a lot of rainfall? So this is this is an example of climate extreme. Okay, if Delhi is getting Delhi is getting snowfall, it is also one kind of extreme that you can see. The another example that I can give you is for the Bhopal. Bhopal has a very nice monsoon system in which it is getting a very uh, 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 like a very good rainfall. So let's say we have 200 mm average. On average, Bhopal is getting the precipitation, but it may be happen that it is getting for one day, or for 1 year it is getting 400 mm. So this will be considered as a extreme. So what I just want to tell you, that at any place we may encounter with the climate extreme, and climate extreme is nothing but just the rare event that we can have. So this again we can understand with the probability density function. So let's say this is your probability density function, and this is the value of temperature. Okay, this is the value for temperature, and let's say this is for Bhopal. And Bhopal, where we have maximum probability, it is, let's say, 35 degrees Celsius. So normally in Bhopal we are getting 35 degrees Celsius. Okay, but we have less probability here. Can you see? Probability is so this is 0 to 1, and here let's say if it is 0.01, and here also. So this part, so the probability is very less, but we can also encounter temperature in Bhopal, let's say near to 45, which we are considering as heat wave, something like that, right? So, and it may be that we are getting the temperature, let's say 0 degree in Bhopal. The probability is very low, so it is rare occurrence. So how we are defining the climate extreme is, we have rare occurrence event that we have, and we are considering them as climate extreme. So the probability is very less, but it can happen. With the climate change, what is happening, that the probability is increasing of such rare events. Okay, and it can happen anywhere. It is not just like that, that some places, it may be that some places are more prone to some climate extreme, but anywhere it can happen, because it is just the tail, low occurrence or the rare occurrence of such events. Okay, is it clear, Geeta, what I want to tell?
Yes, ma'am. Yes, ma'am. Clear, ma'am.
Okay, thank you so much. Okay, so because as I define climate extreme using a probability density function, right? So we need to understand different probability density function and the distribution. The distribution may be like this. The distribution may be like this. Probability density function distribution may be like this. Okay, so some variable may have, or some event have very different type of distribution. We will understand it. Okay, so because we need to calculate, I will give you a lot of questions, and based on that you will see what probability density function is more appropriate for what variable. We will try to understand this. Then we will try to learn introduction to extreme value theory. Um, that I will explain it later, and then the frequency. If it is a extreme, climate extreme, it is not just based on the magnitude, as I told you, if Bhopal is getting 45 or 50 degree. So this is just the magnitude, but climate extreme we can also define in the term of frequency. So let's say we were encountering 45 degrees Celsius temperature in 2 years. Every 2 years we are getting 45 degrees Celsius, but with the time it may be happen that we are getting every year this 45 degrees Celsius. So this is how we can also consider climate extreme in the form of frequency. So we will talk about frequency and intensity in the upcoming MCQs. Okay. Uh, to give you uh, more about idea about why we are talking about probability density function. So these functions are very important to give the answer of some question. I have listed out some question. The first is, what is the probability temperature exceed 35 degrees Celsius? Okay. As again, I'm giving the example of Bhopal. So this is probability, and what we are getting, the highest probability, let's say we are getting for 30 degrees Celsius. Okay, so what will be the probability that we are getting 35 degree Celsius temperature in Bhopal? We must know about this so that we are prepared for it, right? So such kind of answer, the probability can be answered or can be addressed by the probability density function. We will learn about this, right? The second question is, how unusual is 34 degrees Celsius day? So is it very rare, or it is very normal if we are getting 34 degrees Celsius? We can talk this in the form of probability density function again. Okay, this is based on, this is temperature thing. Okay, then next is, what is the probability that daily rainfall exceed 20 mm? If we know that we have dam, or we have sewage pipeline in such a way that city may control the rainfall if it is under 10 mm, or if it is under 15 mm, but we don't have that infrastructure if rainfall is exceeding 20 mm. So we want to know what is the probability that we will get the rainfall that will be more than 20 mm per day. So this again, the probability that we can get using probability density function. Okay, the next is, what is the probability of waiting more than 5 years for another event? So what we do is, whenever we are creating some infrastructure, so it has some lifetime. Okay, and it has some expiry. But before that, we have to keep in mind, if such great event, or let's say if such strong cyclone occur occur in Odisha, then what kind of infrastructure or dam structure we want? Okay, and the what is the probability that it will occur in 5 years, or it will occur in 10 years? Okay, so for that again we want probability density function. The next question is, what is the 50-year maximum rainfall? This again we will address with the probability density function. Can you see in the temperature we can have minus value and we can also have plus value, right? So to address positive value and negative value, we need different probability density function, and most of the time what we use is this bell shape uh, probability density function, which is known as normal normal distribution, right? So what we are learning is that for temperature, because temperature have positive value and also have negative value, so that's why for this we need this kind of probability density function. Here it will have negative value, here it will have positive value, and this is zero because we are standardizing our data set. And this is how for temperature we need normal distribution function, right? Now we are coming to the rainfall. We will have rainfall only in positive value. Either we will not have rainfall, so this is 0 mm, or we will have rainfall, so this is 2 mm, 5 mm, 10 mm. It means we are getting value just in positive. Okay, so it will be like this. You have probability density function. So most probability will be for small value and like this. So let's say this is your 2 mm. So 2 mm has more probability. Okay. And here, let's say we have 50 mm. 50 mm is the rare thing that will happen. So more probability is, let's say, for 2 mm. For 50 mm, the probability is very less. So such kind of function, such kind of distribution is known as gamma distribution, where we have such kind of tail. This is tail, right? So if we have a tail and we have positive value, then such kind of question can be addressed using gamma distribution. It is clear? For temperature, we are having normal distribution. For rainfall, we are having gamma distribution. Okay. For the waiting time, so in how much year this event will occur? So probability of waiting more than 5 years for another event. So one event, let's say, occurred in 2026, then let's say heat wave occurred in 2026, then what is the probability that heat wave we will get in next 5 year also? Or whether, or if we are getting once in 10 year or in 20 years, so this is the probability of waiting. For that we are using exponential distribution, because all questions are related to such distribution. That's why before giving you the MSQ, I'm trying to make you understand what these distribution are. Okay. So if we are having some waiting time, then we are depending on exponential distribution. Okay. Then this is again what is 50-year maximum rainfall and 100-year flood level. This we can solve using either with exponential, and we also have Pareto, generalized Pareto distribution that we will learn. Okay, so such kind of distribution we need. Then we have rainfall exceed. So this is one threshold. Okay, this is threshold that we are keeping. Once rainfall exceed 100 per day, how large can it become? So such kind of question we can address using again GP. So this is GeV, I can say, for this. So this is extreme value, generalized extreme value. And for such where we have threshold, then just remember this is Pareto. So generalized Pareto distribution. Okay. So what we learned is we have normal distribution, we have gamma distribution, we have exponential distribution, we have generalized extreme extreme event distribution, and then we have Pareto distribution. Again, I have one question. If heat wave continue for 10 years, what changes will happen, ma'am? This mostly the impact of heat wave is on human. Obviously, if we are not if we are not constructing infrastructure in that way to so that we can adapt with this heat wave, then a lot of people will die. This is the human impact that we will have. We may have also ecosystem impact, that heat wave will warm the ocean, will warm the river, will warm the pond, and that's how a lot of fishes and all will be may die or maybe extinct. Then there may be long term impact due to uh, because everything is we have circulation, right? We have global circulation, so it may also be affected because uh, how much heat we are transferring to the atmosphere, and that's how whole global circulation system may also be disturbed. And um, so based on that, there is a like thousand of possibilities of what will happen and what will not. It is also depend on GDP. So how much GDP we have, either we are able to buying AC or not, either we have that technology to cope up this heat wave, and based on that human impact will be different for different countries and for different GDP countries. So there is a lot of possibilities for different scenarios. Okay, so with this question, I introduced you with the probability density function. Okay. Uh, okay. So again, I'm giving you some example. If we have temperature, then we are having the normal distribution, and we will see how value vary around mean, as again I showed you. So this is mean, right? This is mean, and mean have highest probability. So our value is near to the mean, or it is scattered, or there is a lot of variability. So this will be covered in normal distribution. Then gamma distribution. So this is again like this. We have positive rainfall that is distributed. Here you can see the positive values. Uniform, we are not working much on uniform because this is at particular interval we have equal probability. Okay, so this is actually not the real case in real world. So this is we are just using when we need a lot of random numbers. If we want to generate, let's say, 100 random number between 0 to 1, so if we are creating random number, then we are having the assumption that the probability of each number will be equal. Okay, so that's how this will be like this. Each value will have same probability, and this is not the real case in the real world. Then we have exponential, time between events. um, One event happened 1 year ago, then when this event will be happened, either in 2 years or 3 years or in 4 years. So for that we are using this exponential we are using this exponential distribution. And then we have generalized extreme value distribution, and where what we are doing is for each year we are having some extreme value. For example, out of 365 days, uh, we learned that the maximum value was 50 mm. Okay, for another year we will also see the highest value of the rainfall. So let's say it is a 20 mm, 120 mm. So we will have the list of values which are the highest value per year, right? So let's say in 2015 the highest value was 90 mm. In 2016 it was 106 or here. So this is something that what we are seeing is that every year we will have some highest value. We are collecting that highest value and then we are fitting it into some probability density distribution, right? So this is GEV. Then we have generalized Pareto distribution, where we have rainfall above threshold. So let's say we are keeping threshold 100 mm. So when the rainfall exceed 100 mm, so 105, 120, 145, 180, so see we are removing this 90. So this is how, and then we are fitting the curve, then we will have this generalized Pareto distribution. So I think this is enough to define the distribution that we have. uh, okay, so as I told you, we can calculate the probability. So let's say we want to calculate the probability when temperature will exceed 35 degrees Celsius. So how we can calculate that probability? So we have formula for different distribution. We have different formulas. So let's say this is your temperature when it is exceeding 35 degrees Celsius, and we have some parameter. So this is your 35. This is mean of all the values. This is standard deviation. Here it is written actually. And this is your phi or phi, you can say. So this is how putting the values in this equation will give you the probability. But before that, you should have the data, the first thing. The second thing is you should have the value of such parameters. So these are the parameters. It is written actually here. So the parameter here, this is mean, this is standard deviation. Again, here you can see we have alpha, we have theta. So alpha is giving us the shape. We'll talk about the shape, and theta will give you the information about the variability or the scale. So the thing is to calculate the probability, but before that we need to calculate the parameters. How we will calculate these parameters? Again, we will have some method to calculate it. Then for the uniform, exponential, so these are how we can calculate the probabilities. Okay. That the question that I gave you in the first slide, we can address such question based on, first we will see what is the best fit distribution for our data set. Secondly, we will calculate the parameters, and third we will calculate the probability. Okay. So let me give you again the steps. So the first step will be to see what distribution is more appropriate for your data set. Either it is normal distribution or it is gamma distribution based on your values that you have. For that, we have a lot of tests also, statistical test. Based on that, we can see which distribution is more appropriate for our data set. Okay, so first we need to see which distribution is fit for our data set. Second, we will calculate the parameter values. How we will calculate the parameter values? From our sample values. Let's say I have 10 days value. So from these values, we will try to calculate the parameter values. For example, this mean and this standard deviation. So we will try to get such values from our sample values. Okay. So if we are able to calculate such parameter values, then we can calculate our probability. Okay. Here, if I want to give more emphasis on this second part, as I told you, I can calculate or I can estimate parameter value from sample. So for example, this is our parameter alpha and theta. This lambda is again our parameter. uh, this xi, this is xi. Xi is also one parameter. So how we can calculate this parameter? So this parameter we can get from sample data. And again, we have a lot of methods to calculate parameter value from sample data. Have you heard about method of moment? There is one method of moment, how we can calculate this. The second is MLR, maximum likelihood method. Then we have Bayesian method also. Bayesian. Okay, and a lot of 4 5 more methods we have. So what we learned is we must know what distribution the our data set is fitting into. The second is to calculate the parameter. Parameter we can calculate from sample, and but we have a lot of methods to calculate this parameter value. The one is method of moment. The another is maximum likelihood method, the Bayesian method. But most of the time we are using either method of moment or maximum likelihood one. Okay, otherwise we are not using much. Then we can calculate the probability. If there is any doubt, you can let me know. Otherwise, we will start with the questions. Do you have any doubt? Even any simple doubt, if you have, you can ask me, because I'm not here just for the formality. I'm here so that you can understand every concept in a nicer way. Everything is clear? Can I get the response? You can ask any question. Otherwise, we will start with some MSQ, multiple select question, as like we have in our assignment for the week 4. Okay, I think I should go ahead. Okay, so my first question is, which distributions are suitable for modeling positively skewed climate variable? If your data is positively skewed, then what kind of distribution you can use for that data set? We have 4 options here: gamma distribution, uniform distribution, exponential distribution, normal distribution, generalized Pareto distribution. And this is MSQ. You need to select multiple. So we will have 20 MSQ question like the assignment question, not exactly same, but similar. So I encourage you to give the answer for this, and I will try to correct it. If even if you are giving me the wrong, maybe this is the way you can learn more. Gamma is one of them. What more? This is MSQ, multiple select. As I told you, what is the probability that we are getting value more than 20 or what is the frequency? So such kind of data set also always have positively skewed data set. Simran, you want to say something? You raised your hand. You can write in the chat box if you want. Okay, so what is positively skewed? Positively skewed is like this. This is your probability density function. You have positive value. So let's say this is 2 mm. Again, I'm giving you example 2 mm. This is, let's say, 30 mm. Here you are increasing. Here it is 100 mm per day value. So what we are learning is that we have high possibility of getting the less magnitude rainfall. High possibility, high probability to get low magnitude rainfall, but very low probability to get high magnitude rainfall. This is positively skewed data set, right? So rainfall data set, the rainfall data set is mostly positively skewed one. Okay, then so based on what kind of question we want to address, we have different distribution. So for example, we want to see what is the possibility that we are having we will get the rainfall more than 20 mm. So for that, gamma distribution is useful. Okay, if we want to know that let's say the extreme event is 20 mm, so what is the possibility that within 5 years we will get 20 mm of rainfall? This we can address using exponential distribution. Okay, this we can get from exponential. So waiting time we can get from the exponential distribution, but the data is same. Data is rainfall data set, right? So we can also use exponential distribution to address the question which is related to the waiting time. Okay, so this is also one of the right answers. Then we have generalized Pareto. Pareto is, if let's say threshold is 100 mm, if threshold is 100 mm, then how many days we can have rainfall more than our threshold? So such kind of answer we can get from generalized Pareto distribution. But again, it is taking the rainfall data set. So this is itself is the positively skewed one. So what I'm saying is that the gamma distribution, exponential distribution, and generalized Pareto distribution are used for positively skewed climate variable. For uniform distribution, uh, this is like this. This is not skewed one. Skewed one is either this is the skewed one, and this is also skewed one, right? But if we have this, it means each value have equal probability. So this is how, this is not possible in the positively skewed data set. So uniform distribution is not among the right answer, and normal distribution also have negative value. And if it is a positively skewed, then it can't have negative value, and we can't rely on this normal distribution. So is it clear that if we have positively skewed values, then we can get a lot of answer from gamma distribution, from exponential distribution, from generalized Pareto distribution, based on what type of question we have? Okay, is it clear that the answer will be ACE? Okay, let me give you here. So the gamma distribution is when your value is more than 0. It is mostly right skewed. And here the main parameter that we need to calculate is alpha and theta. We will talk about this. And typically, if we want to calculate the probability for some particular magnitude of rainfall value, then we can go for this gamma distribution. As I told you, this is flat one. So we are using it just for random sampling. This is not the real case. Exponentially is also have value I equal to 0 or more than 0, and here the parameter is here lambda, and uh, uh, here we can calculate the waiting time. As I told you, we can calculate waiting time using exponential distribution. Normal distribution, as it is from minus infinity to positive infinity, it is symmetrical, and parameter are mu and sigma, and this is for the temperature. I think this is again clear. Then Pareto, just remember Pareto is for the whenever we have some threshold, and this is again tail dependent thing. Here we have three parameters. We have xi, we have sigma, and we have mu. And here we have this is threshold. Okay, threshold extreme. So this is how if the value are positive, the range is positive and skewed, then we can go with gamma distribution, exponential, GPD, but based on what kind of question we want to address from such distribution. Okay. This I think I already have explained. Uh, that first we will see what kind of data we will have, then we will select the distribution, then we need to calculate the parameter value, right? And for parameter value, we have method of moment, we have maximum likelihood estimation, MLE, and then we have probability weighted moment, then we have Bayesian estimation, and a lot. Most of the time we are using either method of moment or maximum likelihood estimation. Okay, based on that we are calculating this alpha value, this sigma value, this phi value, z value. So such kind of values we can calculate from such methods. If anywhere it is unclear, then you can let me know, please. Okay, and then we also want to see whether whatever distribution uh, we have fit into our data set, it is correct or not. For that, we do have a lot of tests. Statistical tests are KS test, Anderson-Darling test. Then we have graphical way. We can see the histogram, QQ plot. I will explain you in later slides. And some information criteria, that is AIC and BIC, that we can use to see whatever distribution we applied in our data set, it is correct distribution or not. Uh, it is giving full information about our data set or not. So otherwise we need to change our distribution, and then we can get a lot of question. We can address a lot of question out of it. Okay, this is not right now important for you. This is again not important for you. This is again not. Okay. Now I'm coming to the next question. You need to tell me about the normal distribution. Which statements describe the normal distribution? It is always positively skewed. It is symmetrical around its mean. Mean and median coincide for the ideal distribution. It has a fixed upper bound. It is commonly applied to temperature data. This is MSQ. You need to select multiple select question. We talked about normal distribution function, right? It was like this. So which statement are correct for the normal distribution? So can you give me the answer for this? Okay, so I got B, C, E. Okay, yeah. Anyone else wants to give the answer for this question? Okay. So, as I told you, normal distribution is from minus infinity to plus infinity, right? So if it has value from minus to plus infinity, then it can't be always positively skewed. So this is the wrong one. It is symmetrical around its mean. This is mean. The highest probability is for the mean and median, right? So this is our mean value here. So, and a lot of values are near to mean, and that's why the probability is higher for the mean, right? But a very small values are for the uh, at the tail. So for example, we have height of a person, height of, let's say, 100%. So what we will get is that most of the people will have height near to, let's say, 5'3". So this is 5'3", and this is your probability. So let's say, and this is your interval. So what you will get is, only few people will have height, let's say, 3 feet, or only few people will have height, let's say, 7 feet or 8 feet. But a lot of people will have value near to the mean. So this is like that. It is symmetrical around its mean. Um um, can you see, this is your 50% area and this is again your 50% area, so there is a symmetry. So, and most of the time we do have normal distribution for most of the example. If we have height of a person, or let's say the eye color of the population, so we can give a lot of example in the real world where we do have normal distribution. Most of the people have black eye in India, but few people will have green eye, or some people will have, let's say, blue eye. So this will be at tail. Few people will have these kind of, and the possible probability will be very low. High value and the mean value will have the highest probability, right? So this is something, it is symmetrical around its mean, and mean and median coincide for the ideal distribution. If it is perfectly symmetry, then your mean and median value will be equal. Okay, your mean and your median value will be equal for the ideal distribution. So this is also correct. It has fixed upper bound. No, it can go up to positive infinity. And if it is going up to infinity, then this is not fixed upper bound. Okay. So this is again the wrong one. It is commonly applied to the temperature data. Obviously, if we are talking about the climatic data set, then among that climatic data set, temperature temperature is having this normal distribution. Rainfall is having the gamma distribution. So different data set may have different distribution, but in real world, 99% of the data set are following just normal distribution, but 1% are either gamma or something like that. Okay. So this normal distribution is applied to the temperature data set. So this is also correct. So based on this, B, C, and E are the right one. Okay. Coming to the next question, which is, which quantities describe the shape or spread of the probability distribution? Variance, longitude, skewness, return period, mean. So again, I'm giving you, let's say you have normal distribution, right? But this can be like this. This is also normal distribution. This may be like this. This is also normal distribution. But can you see the shape? Uh, So the shape is different, and even the spread. So here, can you see the spread is very less? Here the spread is very high. Here the height is very high. Here the height is less. And each these are the type of normal distribution only, but within that, shape and spread is giving you a lot of different information. So how we can uh, assess this shape and spread information from what kind of quantities? uh, uh, one more is correct also. Paras, you gave me A and C, but one more answer, one more option is also correct. You can find out another one also based on shape. You didn't consider the shape. Okay, so okay, let me again. Yeah, E is also right. Gita gave right answer. Okay, so again, let me give you one example of let's say the height of height of 100%. Okay, height of 100%. As I told you, most of the height are near to your 5 foot, let's say 3 inch. Okay, and few values are near to 3 or 6 feet. So this is the one case. There may be case that uh, there may be case that 4 feet and let's say 6 feet also have the probability which is near to the mean. So it means a lot of people have height of 5 5 3 feet, but also there is a lot of people that have the height of 4 feet and 6 feet also. So this is how we are increasing the variability, we are increasing the spread. Our data is not very centered to 5 3 feet, but our data may be scattered, data may have a lot of spread. Okay, so such spread we can get from our variance. Okay, so have you heard about this standard deviation? Standard deviation, can you tell me the relation between this standard deviation and variance? So if we are having normalized standardized normal distribution in standardized, here we are considering mean is equal to 0, then this is our, this part is our 1 sigma, and this is also 1 sigma. Up to this you have 2 sigma, 2 sigma, and 3 sigma up to here. So so it is like that. I'm just giving you the one example. So this part is, let's say, covering 66%. So 66% of your values having 66% of your population have the value near to the mean, and the spread is 1 sigma to 1 sigma, plus minus 1 sigma, you can say. Here you can consider minus sigma. Then these are some percentages, these are some percentages, right? So but if the data is like this, so this is how the percentage of population can change as we are increasing the spread. And this spread can be assessed using standard deviation. Standard deviation is sigma, and sigma square is variance, right? It is variance. Okay, Longitude. Longitude is not related to the probability distribution function, so this is the wrong one. Skewness. So again, the skewness, either it is right skewed or it is left skewed. This will also so the shape of your distribution is also depend on the skewness. Shape is different, this shape is different, this shape is different based on the skewness. Either large values have high probability or your low magnitude have the higher probability. This is also changing the shape. Okay, then the mean, as I told you, sorry, here I can draw. It can be this one and it can be this one and it can be this one, and here the mean is changing, right? So based on these things we can tell the shape and spread of the probability distribution: mean, skewness, variance. Return period is again not related to the probability distribution, but it is related to your some event. If you have any doubt, you can just let me know. Otherwise, we can go to the next question. Okay. Okay, I already have given the answer for this. This is which distribution is particularly appropriate for modeling waiting time between independent rare events. So for the waiting time, we already understood that this will be your exponential distribution, right? So if one event happened in 2026, then when this will happen, so what is the probability that it will happen in 5 years, or what is the probability that it will happen in 10 years or in 15 years? So if we want to calculate the waiting time, then this is exponential distribution on which we are relying on. Okay. Okay, the next question is related to non-stationary. Which property can make climate data non-stationary? Changing mean, fixed variance, time varying variability, long-term trend, constant distribution. If you do not know about non-stationary, I will let you know. But before that, I'm expecting that you are giving me some answer wrong or right. It doesn't matter. Okay, so I got two answers. These two are right, but one more is also right. Yeah. So okay. We have three options which are right. Changing mean, time varying variability, and long term trend. So again, let me make you understand what is it. So for example, again we have 100% and we are seeing the height of 100%. Okay, then what we learned is that the mean height in India is 5'3". Okay, mean height is 5'3". But what we and this mean height was till like we collected 100% data for 2026. Okay, if we are collecting the data of data for 2030 for 100%, and it may be that due to climate change, due to a lot of fertilizer we are having in our field, due to our lifestyle, we are eating a lot of junk food, right? If we are if we are eating a lot of junk food, then it may be that in 2020 the 100% mean height is 5'1". So it means over the year the height of the person is reducing. Okay. There is a lot of, or you can say, like, one more example is uh, the color of your hair. Okay. Initially, you people consumed, or the people in the past consumed very healthy food, and that's why a lot of people of particular category had black hair. But over the year it has been changed to the white hair. Okay. uh, for the same age category. So this is something that the mean is changing, and if mean is changing, then this will be known as your non-stationary. The data is not stationary, data is not constant, it is changing with the year. Okay, so your data is not following this distribution, but your data is kind of, it is increasing or it is decreasing over the time. So let's say this is your year, and this is the height of the person, and what we learned is that the height of the person is decreasing over the year, and that's how the mean will be changing, and the data is not stationary, data is changing. This is not constant. The same example we can apply to the temperature. Initially the mean temperature was, let's say, 30 degrees Celsius over the India, but over the time it is increasing, and now the mean is 33 or 35 degrees Celsius. So this is, the data is not stationary, data is not constant, it is changing. So if the mean is changing, as I told you with the height example and the temperature type, so this is, the data is non-stationary, so it will be very difficult for us to apply this normal distribution or any kind of distribution to this data set, because each year data set have its own normal distribution, but it is increasing with the time, it is changing the mean. So this is non-stationary. Then fixed variance. If it is a fixed variance, then this is stationary. Fixed means it is constant. The spread is constant. Then we can't call it as a non-stationary. Time varying variability. For example, for this example, let me take you one another example. For the temperature, what we learned is that out of 100 days, out of 100 days, we had for 90 days, we had temperature, let's say, between 30 to 35 degrees Celsius, and for 10 days left we had temperature which is less than 30 or more than 35. Okay, but now let's say in 2030 it can be happen that for just 40 days the temperature is 30 to 35, but for 60 days the temperature is either less than 30 or more than 30. So this is how we are increasing the variability. Okay, we are increasing the variability, and if this is happened, then again your data is not stationary, so this will be considered as non-stationary. Long term trend, as I told you, it is increasing, the height is increasing or decreasing, let's say over the year. Then this will be the long term, and this is like the subset of it is the changing mean. So this will also consider as the non-stationary data set. So how we can cope up with this? So for example, this is your temperature data set. So this is your temperature and this is your year. Temperature was rising like this and this and this, and then it shift, and then it is start to increase. So what we can say is that this is your break point. So what we can do is, we can analyze this part separately and this part separately, because the data is non-stationary, data is changing with the time. So we are assuming that this 10 years the data was not changing much, so we can calculate, or we can fit into some distribution for, let's say, 2000 to 2010, and then again we can have another distribution, and we can have this distribution for 2010 to 2020. So this is how we can divide our data set into uh, two groups, and then we can calculate separately the distribution parameter values, and we can estimate the things, because here the probability will be very different from this probability, and that's why we need to separate these two by some groups, by the year groups, and that's how we try to address the non-stationary in the climate data, and we separate most of the time. Okay. And constant distribution, if it is a constant, then how it can be non-stationary, right? So if you have any doubt on this question, you can let me know, otherwise we can go to the next question. Okay. The next question is, which methods can be used to deal with non-stationarity in climate data? One I told you, more you can tell me. Detrending, ignoring long-term trends, time-dependent models, dynamic distributions, assuming constant parameters. What are different methods by which we can deal with non-stationarity in climate data? Yeah. So I get response from Paris, that is A, C, and D, and yeah, these are the right options. Let me explain why it is. So again, I told you, we the mean is changing with the year. Okay, mean is changing with the year. So what so the one method is, if we are subtracting the value from mean. So let's say we have temperature data 30, 35, let's say 40, 28. This is your data. This is your one data, and the next data is 30, 40, 45, 50. So what I can say is that this was the data, let's say from 2010 to 20, and this is the data from 20 to, let's say, 30, 2020 to 2030. Okay, and clearly we can see that the mean, or the value is changing. Okay, so what we will do is, we will calculate the mean of these value, or combinedly we have, let's say, 10 values. Combinedly we have 10 values, we will calculate the mean, and let's say the mean value is near to 35. We will subtract each value from 35, so this will be -5, 0, 10, then this will be -7, this will be -5, -10, sorry, 10, 15, and 20, or yeah, 5, 5, 10, and 20, 15. Right. So this will be our value. And now we will fit these value into our probability density distribution. Okay, so we will fit these value into some distribution. So what we are doing is we are removing the mean, and that's how we will have the value from minus 15 to 15, and then we can fit into some distribution. So this is how we are detrending. Detrending. So this is something like that. Again, I'm giving you one example. You know that this is, let's say, January, February, and December. And this is your temperature data. You know that in January we have low temperature, and in now we have high, and then we are low. And every year we will have such kind of up and down peaks. So what we will do is we will subtract it from the mean, so that your per year data set is not like this. If we are subtracting it from mean, so this will be like this only. Okay, so this is how we do detrending of the data set. So we can do detrending to remove the non-stationarity. Ignoring long-term trend. If we are ignoring, then not, we are not dealing with non-stationary. We are keeping the non-stationary data in our climate data set, right? Time dependent model. There are some models that are considering the time, and based on that it is applying the statistics, it is applying the distribution. So this is how, what I told you, we are separating the time and then we are calculating the distribution. So this is how we can deal with non-stationarity. Dynamic distribution, this is again based on some equation, based on some models, we can remove this non-stationary with more advanced equations or statistics. So this is again, we can deal with non-stationary, assuming constant parameter. No, this is not the right one. Okay, now we have more terms, two terms, block maxima and POT approaches, and you need to tell right statements for these two terms, how we can differentiate these two terms. Block maxima retain one maximum per block. POT requires a threshold. Block maxima generally use GPD. POT examines threshold exceedance. POT must use annual data only. POT is peaks over threshold. Let me tell you. Peak over threshold. One more option is right. You selected two. Okay, yeah. So the right answer is ABD. Now let me tell you how. So if we want to see how our extreme values are changing, again, let me give you one example. Uh, uh, One example of temperature. So let's say we have temperature data set, right? We have temperature data set. For Delhi, we are considering Delhi as 1 point. Okay, we are considering Delhi as the 1 point. So for that 1 point, we have some station and we are getting the data set. Okay, so in 365 days, it means for 1 year we will have 365 values. Okay, but what if we are selecting, so we will have 365 values for 1 year, but we are selecting just one highest value, one highest value. So let's say we calculated such kind of data set for 20 years. So no doubt we will have data 365 into 20, but maximum value will be 20. Each year we have one maximum value. Okay. Now these are our maximum values. Now we are fitting it into some distribution. Or if we are seeing how these values are changing with the year. So this is your highest rainfall, and this is your year. And it may be that highest rainfall every year, the highest rainfall magnitude is increasing. Okay, so if we are selecting the highest value out of a bunch of value every year, then this will be your block maxima. Okay, and with this method, block maxima, you can talk about the extreme values, how extreme values is changing with the time, what is the possibility that with in 2013 the value will be this magnitude. So such kind of question we can address. Okay, so this is your block maxima. Then the next is peak over threshold. So peak over threshold is that I'm taking the example of heat wave. Okay, I'm taking the example of heat wave. Let me remove this. Uh, IMD, that is India Meteorological Department, is describe the heat wave in the plain area when temperature is more than 40 degrees Celsius. Okay, when temperature is more than 40 degrees Celsius. So what we are doing is, this is, let's say, our 1 2 365 days, and this is for 2026. So in 2026 we have 365 days, and we are having the station that is taking the data of the temperature, and then you have like this and this and this and this and this, and then it will go down, and this is your 40. Let's say this is your 40 degrees Celsius. So what we are getting is that out of these 365 days, it is, let's say, 2 days when we are getting the value more than 40 degrees Celsius. Okay, so for 2026, we are getting not just one highest value, but we are getting two values. And likewise, for 20 years, we will have for 20 years we will have not just 20 values, but it can be more. It may be that in 2027 we do not have any value that is exceeding 40 degree, or in 2028 it may be that it is 10 days that we are getting value more than 40 degrees. So it means that every year we may have some values, collection of value, which is based on the threshold. We are putting the threshold 40 degree because above that we are considering it as a heat wave. So collection of that values, and then we are plotting it into some fitting it into some distribution. Then this will be this is your peak over threshold approach. Okay, so now if I'm seeing Block maxima retain one maximum per block. As I told you, per block, let's say per year we will have just one value. We will not have two value or three value, because the maximum value can be just one. Okay, the highest value will be one. So we will have one value per block. This is right. POT require a threshold. As I told you, it need the threshold. Either we are putting the threshold 40 degree or 45 and 50 degree. So based on threshold, POT requires some threshold, and we again have some methods by which we can see whatever threshold we have kept, it is right or not. Okay, we will learn about these method also. Then block maxima generally use GPD. As I told you, Pareto is using POT. It is based on some threshold. POT, sorry. GPD distribution is based on peak over threshold approach. Okay, so this is the wrong answer. POT examine threshold exceedance. This is what we are doing with the POT, right? We are seeing how many days it exceeded the threshold, right? So this is what we are doing with POT. POT must use annual data only. No, this is not necessary. We can have annual data, we can have daily data, we can have monthly data. So based on our need, we can have any kind of data set that we can use for the POT. Okay, so this is again not the right option. If you have any doubt about block maxima and POT, you can just let me know. Otherwise, we will go to the next question. And one more thing is that this block maxima and peak over threshold approaches are the part of your extreme event theory. So generalized extreme event theory. So this is GET, or extreme value theory. We also so this is GEVT. So to calculate the extreme, either we can adopt block maxima approach, or we can also adopt POT approach. It depend on how, what question you are addressing, right? So for example, if I want to address how the heat wave is changing over the year, and for heat wave, I'm having some threshold that we are considering heat wave when we have value more than 40. Then for to calculate that extreme, or to know about this extreme event, we will use POT approach. Okay, but if we want to see how the maximum value of temperature is increasing or decreasing over the year, and how the distribution is changing of the highest value, okay, then we will rely on this block maxima. So this is based on what kind of question you are addressing. Based on that, to calculate extreme events related things, we can have any kind of approach that we can use. Okay. Again, I already have given you the answer. Which distribution is most directly associated with annual maximum series? So if it is annual maximum series, then I told you this is GEV. So this is generalized extreme event theory, in which we can have this maxima and this POT. So we are using GEV. Poison is for counting the extreme event days. So this is mostly for counting part, right? Gamma is not for annual maximum. Gamma is just seeing how like what is the probability that you are getting temperature or sorry, precipitation more than 20 mm. So this is like that. Exponential, this is again the waiting time. Binomial is very different, and most of the time climate variable doesn't fit into this binomial distribution. Okay, so this is the function. This is the cumulative density function for your GEV. generalized extreme values. And here what we can see is that we have three parameter. This is z, then we have this one, this is mu, and this is your sigma, right? So mu is your parameter mean or the population mean. Sigma is your standard deviation, so population variability we can see. And z, so z is your shape parameter. So what we can see is the mean is your location parameter. It will tell you the location. Sigma is your scale parameter. It will tell you the variability. And z is your shape parameter. It will tell you the shape. So, for example, uh, this is this one or this is this one. So when your mu value, so mu is mean value, so your mean is shifting left or right, so we can get some information out of this. Sigma is your spread, so either it is like this or it is like this. So spread, sigma will tell about your extreme value have some whether the variability in extreme value is increasing or not. Then shape, it control your tail behavior. So let's say your tail can be like this, your tail can be like this, a very exponential drop, and your tail can be, initially it was going slowly and then it is exponentially drop. So so this is about your extreme values probability. So from here what we can see is that low value have high probability. Then then here up to here it is just that your high value have low probability, but here it is exponentially decreasing the probability from here on onwards. So this is how it will tell about your tail behavior. So based on this I have questions. Okay, if your shape parameter have value more than 0, then we are calling this distribution net as Fréchet type, which is having very heavy upper tail. So this is like that. Okay, so this is when you have z value more than 0, then it will have very heavy upper tail. If your value is equal to 0, then this is the case of gamble, and so here we will not have much tail, so this will be like this only, the less tail, so it will be more towards the symmetry. If your z value is less than 0, then the distribution will be Weibull type, and in Weibull type you will have a finite upper bound. Fourth question answer, which one is the fourth question? Mm, yeah, it was exponential. Waiting time, exponential. Okay, so we talked about the based on this xi value, we can tell about the tail. Okay, and based on that, we have some questions. Okay, so if we have value more than 0, then this is Fréchet. We have heavy tail, we do not have upper limit, and this is very large extreme possible. So extreme can be possible very large, something like that. Okay, if your z value is 0, then this will be gumble, or this is very light tail we will have, or exponential type we will not have upper bound, and it is intermediate tail behavior. So this is like like this only. Then we have Weibull. It is bounded and it has some upper limit and it has some finite theoretical maximum. So based on this, we have some question. Yeah. So if we have positive GEV or GPD and the shape parameter has positive value, then it generally indicate what? A heavy bounded upper tail, heavy tail behavior, freshet type behavior, zero variability, a finite endpoint. So if your xi value is positive more than 0, then you can talk about the tail. Okay, let me see the answers. Okay, I didn't get any answer, but okay. Based on that table only, I think you can give the answer. So if we have xi value more than 0, it means it will have upper tail that is very heavy. If upper tail is very heavy, it means that no doubt the probability of your extreme is very low, but the extreme magnitude may be very high. So let me give you one example. So if we are getting, let's say, 55 degrees Celsius temperature, this is very rare event, but it can happen. But it can happen because here because the tail is very long, right? So the extreme is not only up to 45. We are not considering we have extreme at 45 degrees Celsius also, but the value may exceed more because the tail is very long. So this is how, when the value is, when this shape is more than 0, it means your tail will be very long, and that's how your extreme event no doubt has very, it will be very rare event because the possibility will be very low, the probability density function value will be very low, but the magnitude may be very high. Okay, it is not just 45 degree, it can reach to 50 degree, or it can reach to the 55 because the tail is very long. This we can see using our xi value. If it is near to 0, this means it is the gumball. So we are exponentially decreasing, right? uh, so this is intermediate tail behavior. From where we can get is that no doubt we will get extreme event, but the magnitude will not be much high. It may limit to 45 or 50, but it will not reach to 55 degrees Celsius because tail is exponentially decreasing. It is not like that it is going down and down and down, and slowly it is like stretching itself. Okay, then we have Weibull, where we have bounded upper tail. Uh, Up to some point, this is going down, and then it can have the exponential decrease. Okay, so based now let me go to that question. So if it is a positive xi value, then it is a heavy tail behavior. As I told you, this will go very long. Then such kind of again, let me go back. Yeah. So this is heavy tail, no limit, no bound, and this is Fritchett type. Okay. So heavy tail, Fritchett type, uh, zero variability, no. Finite, no, it has infinite endpoint, and this is not bounded, right? So B and C will be the right answer. If you have any question on it, you can just let me know. It will not be E, because as I told you, the value, so the tail is going down, 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 and we are seeing that it is going till infinity, right? So it doesn't have finite endpoint, so that's why E is not the right answer for positive shape parameter xi. Okay. If your parameter value, the xi parameter value is negative, then what information you will get? Extremes are bounded. It represents fractured behavior. It is associated with Weibull type tails. The upper end point can be finite. It necessarily gives an exponential tail. If your xi value is negative, then what? That's why, see, that's why we are fitting our distribution, because in distribution we have a lot of parameters, and if we are able to calculate that parameters, we can have a lot of information out of this parameter. The one example is our shape parameter xi. The xi can give you a lot of information about the data, about the trend, about how your extreme is changing, or what property extreme event has. So that's why it's very important for us to fit our data into some distribution, and we can have a lot of information about the probabilities, about a lot of things we can get out of it. Okay, so I got answer from Paris, which is correct. That is ACD. We already have seen that if the value is negative, then we extremes are bounded. Then this is not Fritchett behavior. This is the Weibull type tail that we will get, and the upper end point can be finite. It can be stopped at some magnitude. Okay, it necessarily give an exponential tail. No, it is sometime it can give, sometime it is not. But exponential tail is mostly when xi value is equal to near to the zero. Okay, so exponential tail is for xi value is equal to zero, not for the negative values. Okay, again, I already have given the answer, but see, which quantities are needed to calculate a GEV return level? So, for the return level, we need shape parameters. Uh, we have, it may be that I have this explanation. Let me see. Okay, I don't have explanation. Okay, yeah. So, GEV return level. So, for the GE return level, we are using mostly GPD distribution. So, this is generalized Pareto distribution. And in this generalized Pareto distribution, we have parameters that we are calculating is mean. We are calculating mean. We are calculating sigma. We are calculating xi. And based on this value, we can calculate time. This is 1 by lambda. Okay, and this is your return period. You can tell the possibility, what is the possibility, or the possibility percentage that we will get that event, let's say in 5 year or in 10 year. We can give the probability. of that thing based on your return. This will give you the location, this parameter, the scale parameter, this is your sigma, and shape parameter is your xi. So these all quantities that we needed to calculate ZEV return level. Initially, if we will get these things, then we can get this part, and then we can address a lot of questions out of it. Okay, I again gave you the answer for this. 150-year return period correspond approximately to which annual exceedance probability? So, as I told you, here T is equal to 1 by lambda. And if it is, your annual exceedance probability will be 1 by T. So 1 by 50. And if we are having, so this will be 0.2, and if we are calculating it into percentage, then 0.02, and if we are calculating it into some percentage, then this will be 2%. So it means we can say that it is just 2% probability of some event that it will be returned in 50 years. Okay, something like that. So the return period T, the approximate annual exceedance probability, so this P is equal to 1 by T. Oh, so it was not lambda, it was P. Um, so if T is equal to 50 years, then P is equal to 1 by 50, and that's how we can convert it into percentage, and this will be the 2% probability. So this is how not only, we can calculate the probability not just for 50 years, we can calculate probability for 30 years, for 20 years, and for any time period, any return period, right? So this is the advantage of using the distribution. Okay, which statements about return periods are correct? A 100-year event can occur in consecutive years. A return period is based on probability. Return year event must occur once every century. A larger return period generally corresponds to rarer events. Return period are always constant in a changing climate. I think this is the simplest one that you can answer. About the return period. So, for example, we are saying that in India, the return period for flood for the past year, it was 2 years, or let's say 3 years. So on average, we are getting flood in 3 years, every 3 years. So yeah, or you can say that based on El Nino, because El Nino is happening in 3 to 4 years, and if El Nino will happen over, and it will have some impact on India, and that's how what we can see is that the return period for drought is, let's say, 3 to 4 years. So every 4 years, let's say every 4 years, we may have drought, based on some studies, because the drought is related to the El Nino. So this is about the return period. So I got answer. Um, this is ABD, but not ABC. Let me explain you how. A 100-year event can occur in consecutive years. As I told you, no doubt, we can say that the drought, the drought can happen in 3 to 4 years, but it can also happen that drought is happening back to back. Okay, so it is like that. Your 100-year event can also occur in consecutive years also. So this is how it is climate change. Because of climate change, the event that had the possibilities that that event will happen, let's say once in 100 year, but it the frequency can be increasing, it can happen in consecutive year also. Return period is based on probability, obviously. So probability, p is equal to 1 by t. 100-year event must occur once every century. No. So there is a lot of study that are saying that 100-year event, if there was one frequency that we had, now the frequency is increasing. So it may be that 100-year event, now it is happening after, let's say, 10 year, after 15 year, and the frequency is increasing. So it is not necessary that it will occur every century. Or it may be that for 100 year we are not getting that one, or if we are getting more than one. So anything can happen, right? So C is not the right one. Larger return period generally correspond to rarer events. Yeah, obviously. So let's say we are having the earthquake, which is more than 9 or more than 8 richer scale. So this is very rare event. I don't think in last 10 years it happened that it is the earthquake is exceeding the richter scale of 8 or 8.5. If it will have very big impact on India. So and such kind of event, which have very larger period of return, or larger return period, these are very rare events, so we can estimate it from it, right? Then return period are always constant in changing climate? No, a return period is changing. Initially the return period was, let's say, 5 year, but now the same event is coming in 2 years or in 3 years, so the your return period may also be changing. So that's how A, B, D are the right answer. Okay, then now we are seeing that we talked about the distribution. We have some data and we are fitting that data into some distribution. But how sure you are that that particular model is correct for your data set? So it is based on some test, based on some visualizing thing that we need to do. Which tools help evaluate whether an extreme value theory model fits the observed extreme? QQ plot, Anderson Darling plot, mean residual life plot, return level plot, Fourier spectrum only. So the thing is, again, let me tell you. So this is your precipitation and this is your tail. Okay, and this is, let's say, your 200 value, and probability is 0.1. Okay, so we are saying that the probability is just zero point 0.1 or zero point 0.1 that we will get 200 of rainfall. Okay, based on this distribution, we can tell the probability of 45, we can tell the probability of 100 everywhere. But it may be that your real data is lying here, your data is lying here. So here what we can see is that, so let's say this is 120 but 120 is having high probability. It means that the distribution that we fit into our data set is not giving exactly our observed extreme. So there may be some discrepancy. We need to fit our data, fit our data into that distribution very carefully. So for that we have to apply some test whether this distribution is giving us this distribution is uh, fitting our data in nice manner or not. So this should be like this. Okay, so for that we need to test a distribution function is fitting our data in better way or not. So what test, what plots we can do to see that these model are fitting our observed extremes or not. So the one is QQ plot. Okay, let me tell you now. Uh, the right answer is one is QQ plot, that is quantile plot. So what we are doing is, so let's say we have 20 values, right? We have 20 values and we are fitting this 20 value into some distribution. Okay, so we are calculating the quantile value of these 20 values independently, and we can also calculate the quantile value of the distribution, and then we will see whether the distribution quantile value is same or similar to our observed quantile value. Okay, so it should be like this. This is your quantile value of your distribution. This is quantile value of your observed value, and then you will see this should be like this. Even if it is like this, it will work. Okay, so this is your QQ plot. If your quantile are not matching, it means it is not the distribution is not perfectly seeing the extremes. So for example, the 90th percentile of your 20 value is, let's say, 105 mm, but it may be that your distribution is giving the 90th percentile value is 120 mm. So there is a discrepancy. Observed value, what is the 90th percentile of the observed value? What is 90th percentile that we calculated from our distribution, not just from the values, from the fitted distribution. So if there is a difference, then we can say, okay, so this model is not fitting well our data set. Okay, then the second is Anderson-Darling test. This is again, so here this is visual thing. Visually we can see here this test have, this is statistical test. Based on your p value, it will tell whether your model is correct or not for your data set. Okay, it will again see the percentile values, but it will have some hypothesis. It will accept or reject the hypothesis, and based on that it will tell, okay, this model is fitting your observed extreme or not. Okay, so this will give the p value, and based on that you can reject or accept the model suitability for your data set. Then you have mean residual life plot. This is not for the model fitting, but this is for to see whether whatever threshold in POT you are having threshold, right? So whatever threshold you have selected, it is right or not. So this is for POT, but it is not for the model fit. Then we have return level plot. So again, we are seeing that if one event is returning in 5 years, if we are having the distribution, does the distribution also showing the return level of 5 years or not, or it is showing the return period of 4 years? So we will see the difference of this return level also, and based on that we can see our model is correct or not. Fourier spectrum is very different, and we are not actually much aware about this Fourier because this is not of use for EVT, that is extreme value theory models. So the answer will be ABD. if you have any query related to this question, you can just let me know. We will take one more question, up to 15, and then we will go for dinner. And five left question we will solve in next week. This I already have talked to you about. This is your QQ plot. Observed versus theoretical quantiles value, Anderson-Darling test, difference between empirical and theoretical cumulative density function. It will see the function of your observed and your theoretical one. Residual life, as I told you, this is for POT. A return level, as I told you, extreme magnitude versus return period. Fourier spectrum, this is about variance power across frequency, that I'm not much aware. Okay, then we will stop to the fifth question, and this is, what is the main role of mean residual life plot? As I told you, it will help us to fix the threshold. If we are taking the threshold 40 degrees Celsius, then this threshold is correct or not. So for that, we are using this mean residual life plot. So it will select a POT threshold, and let me show you how. So let's say this is your threshold, and this threshold is 100 mm. So you will select all the values that are more than your 100 mm. Okay, then so this is how you will calculate the exceedance, and then you will calculate the mean of this exceedance, approximate the mean exceedance, and the mean value that you got is from the distribution, and you will see also many threshold value you will have, and you will compare it, and then based on that you can see here that even if we are increasing the threshold value here from 70, 80, 90, there is not much difference. It is linearly increasing only. So it is like we can select this 60 or 70 as the threshold. So this is one way by which we can select the threshold. So I think I should stop here, and till now we will meet next week again 6 to 8, and we will solve remaining 5 question. And if you want that I take only the question of week 5, then I can upload this remaining 5 questions on Google Drive, so you can access it and you can see the answer of this remaining 5 questions, so that we can start with new week questions. So you can just let me know what do you want. You want the discussion, or you just want the question and answer in the slide or PDF format that I can provide. So thank you so much for the patience, and we will meet next week, same time 6 to 8, and then happy reading and have good food and good health. Show the 50. Okay. What is the main role of mean residual life plot? So this is to select the threshold, peak over threshold. So the main role of mean residual life plot is to select the threshold. Okay, so thank you so much. Now you can leave the call, and if you have any query, you can just let me know. You can anytime mail me about your queries, and yeah, thank you for your participation.